Okay. So here we get the gauge transformation of the basis. So here we find that for this piece is common for all the edges. So you make a product of all the edges from 1 to 6 neighboring this vertex, and then you factor out a common factor which depend on G of V. Yeah, so it doesn't, well, of course those labels depend on E, but these the group element here, it doesn't depend on E, it's only depend on V, because this is a gauge transformation. All right, so now let me consider certain linear combination of these matrix elements by making some coefficients and sum over this M index. Because here you can see that this K index is sum over this K, and this M index is sort of relates to this vertex and this factor. But this factor is related to the vertex. Okay, so now let's consider linear combination. Well, let's consider what we call a tensor. Tensor J1, J6, and M1, M6. Well, clearly this is a, if you fix J and M, this is just a number. This is just a coefficient. But why we call it tensor? And because it depends on different M's. Yeah, so this is usually we call the tensor. You can view these M's are just abstract index. This is what we learned before. What is tensor? And you get some abstract index M. So here this J, or you can write this J1 C and J1 to J6. It is a tensor, or it's the state, belongs to the tensor product Hilbert space J1 to J6. Well, this is it is a rank 6 tensor. But in principle, well, probably it's better if I put it. Let me see. Well, in my notes, I put the M downstairs, but probably according to our convention for the tensor, I should better put the indices upstairs. J6. Okay, so here this J1 to J6 is just a label, labeling the Hilbert space this tensor belongs. So this is a tensor, and the tensor components is M1 to M6. So more precisely, this C can be expanded in basis, sum over M's, J1, J6, M1, M6, by J1, M1, J6, M6. Okay, so this is a tensor which couples 6 angular momentums. Okay, so you should be familiar with that either in quantum mechanics or your previous experience on tensors. Okay, so now so this is, at this moment, this is just an arbitrary tensor. Yeah, this is the coefficient C is just arbitrary. So now let's consider a linear combination of this tensor with respect to the basis. Okay, so now let's make linear combination. Consider linear combination. Okay, let's take a sum M1 to M6. So here this M1 to M6 is going to sum with this ME. C J1, J6, M1, M6, and then you multiply product over E from 1 to 6, I to E, NE, HE, other factors. So this is the linear combination of our previous bases. Okay, and right, and this is just our previous basis. So here now we just this is just a t, right? This is just t. Okay, so here what I'm doing is just making linear combination of previous states. Okay, so now let's consider this gauge transformation. Yeah, and the gauge transformation, we know the gauge transformation of the basis already. Okay, we just plug it in. 1, 6, 1, 6, 6, product in pi. So the gauge transformation factor out a pi of g, pi of gv. Ke gv pi je ke and other factors. Okay, so now you can see that at least you can make it gauge invariant if at vertex v. So if this quantity equals to this quantity. So if this quantity equals and c multiplies this gadget depend on gv and then summing over m, if this action doesn't change c, doesn't change this tensor, then at least at the vertex v, you get gauge invariant. Okay, so you get gauge invariant at the vertex v if you have this identity, if you get this relation, c c m1 m6 j1 j6 6 je ke v sum over m. So suppose this action, this operation, you can view this is an operation on this tensor C. Suppose this operation leave this tensor invariant. So this it should be k1 to k6, k6 and j1 to j6. Then you get gauge invariance, because if you plug in this formula back to the formula above, you just recover the previous formula, at least at the vertex v, right? And of course, you get an additional factor of that, but it relates to some other, some neighboring, some other vertices. So suppose you have this formula locally at the vertex v, and you get gauge invariance. Okay, and suppose you have, so here we only consider single vertex and we don't discuss other vertices, but suppose every vertices you have, you impose this tensor and you have linear combination of your basis by using this tensor, and this tensor satisfy this property, and then at every vertices you get gauge invariance. So all the argument is local. All the argument is locally at vertices. Suppose every vertices you impose this tensor, make linear combination, then every vertices you get gauge invariance. And all your gauge transformation is at vertices, so you get gauge invariance everywhere. Okay, and now let's look at, so let's call this equation 1. And this equation 1 is actually what we call a invariant tensor. So this means that this equation 1 means that C J1 J6 is an so-called invariant tensor in your tensor product Hilbert space. J6. Okay, so here you can see that as I said, this is kind of operation. The left-hand side of this equation 1, it is just a operation on this tensor C. And what is this operation? This is just an SU2 group acting on this tensor. So this tensor is a representation, live in a tensor product representation space. Okay, and the each Hilbert space Vj carries a representation of SU2. Okay, and these operation on this tensor C is nothing but the tensor, so-called tensor product representation. So this is a tensor product representation acting on this Hilbert space and act on your state C. Okay. How to see it? It is a tensor product representation. So this, okay. So at every every Hilbert space Vj, you have a representation. So this means this operator act on Vj, Ij, G, okay, and then the tensor product representation Vj 1 tensor 6, and these operator, this is for any G belongs to SU2, and this pi of G is a representation matrix act on the or operator act on V of J, and the tensor product representation is just a tensor product of the operators. J1 pi J2 of G pi J6 of G. Okay. Again, for any G belongs to SU2. Okay. So this is called product representation. Tensor product representation. This is called tensor product representation. So here, given any group element G, the tensor product representation is using the same G. Yeah. So its point is that it's the same G. Yeah. And right, and same G give a representation matrix or give an operator act on individual factor of representation space. And so here you can see it is exactly the same G of V, yeah, the same G, and you got the representation matrix and act on this tensor. Now this am contraction, it means that it's act on the tensor state. All right. And this equation 1 just means that under this operation, this tensor C is invariant. It's invariant. It means that this C is an invariant tensor in the tensor product representation. Okay, and now I can put this formula 1 in another formula which is probably more familiar for you guys. Let me put a lemma. So on each representation Vj E, well, there exists, because this is representation space, you can define your angular momentum operator. So Je, this angular momentum operator is Je1 hat, Je2 hat, and Je3 hat. So E is just a label for angular momentum operators, and you have different copies of angular momentum operators on different edges. So that's why you have coupling of angular momentum. And then this equation 1 is actually equivalent to this statement. So you have on every edges, you have 6 edges around the vertex. On every edge, you have these angular momentum operators 1, 2, and 3, J1, J2, J3, yeah. And then you can consider the total angular momentum coupling these 6 edges. So you can consider the total angular momentum sum over E from 1 to 6 vector JE, yeah. And you consider this state, this operator act on your tensor J1, J6. Yeah, remember this. We define this tensor to be a tensor product belongs to the tensor product Hilbert space. Yeah, so this is a state which couples 6 angular momentums. Yeah, so you can consider the total angular momentum of this state. J6 belongs to J1, J6. Okay, and it equals to 0. The total angular momentum equals to 0. Yeah? So the equation 1, we call C is invariant tensor. Yeah? It's equivalent to say that C has total angular momentum 0. 0 total angular momentum. Total angular momentum state. All right, and this is your homework to prove this. So what you need to do is just using the relation between this G and the angular momentum. So this is a representation of sp2 group element G, and this G, this representation relates to angular momentum operators, just like here, just like here, it relates to angular momentum operators, and then you just using this invariance, and what you need to do is just making derivatives of left and right on those parameters alpha, beta, and gamma, and you should recover this zero angular momentum state condition. So this is it's very simple proof. Okay. Okay. So now, so this state C J1, J6 satisfying. Well, this is the invariant tensor or zero total angular momentum state. Satisfying 1 or equivalently 2 is what we usually call an intertwiner. Intertwiner. This is just you can, well, of course you can call it invariant state. You can call it zero angular momentum state. You can also call it a intertwiner. Most of the loop quantum gravity literature, people call this state an intertwiner. And span the invariant subspace. I and V. So clearly this equation, you can see this equation is kind of eigenvalued equation with 0 eigenvalue. So and clearly it defines a subspace in this Hilbert space. And the subspace is what we call this invariant tensor space. INV J Bj1 Bj6. This is a subspace of J1 Bj6. Okay, and this is what we call space of intertwiners. Okay. All right. Okay, so now we see that in order to construct gauge invariant wave functions, we just need to insert these kind of intertwiners at all the vertices and making contraction with the basis, with previous basis. We just need to do this kind of linear combination. Then we get gauge invariant states. Okay, so now we can construct the basis of gauge invariant wave functions. Gauge invariant wave function. Wave functions. By the way, so there is one homework. I think, is there any other homework? Yeah, there is another simple homework in this lecture. So this homework is due next Friday. So you submit your homework before next Friday. Yeah, so, but of course, this homework is not taking into account of the grade in general relativity class. This homework is already beyond the general relativity class. But if you submit the homework, I prefer you submit the homework before next Friday. Okay, so now let me write down the basis of gauge invariant wave function. So this is again labeled by T. The label for T is gamma J. Gamma is just our lattice, and R. So before it was labeled by J, M, and N, but now I don't have M and N anymore because this M, you can see this M is contracted by this C. The magnetic quantum numbers M and N, they are contracted by the invariant tensor. Again, it's dependent on all holonomies. This is defined to be, we first make a product of all the edges and pi J E H E. So now, well, because it is most of the time complicated to write those indices, so I'd rather skip those indices, but tell you how they are behaved. And here again, I skip indices J and I. Okay. And so here you have to, there are three indices. Maybe, well, at this moment, I still write the indices, ME and NE. NE, okay. And you can view that, let's say there's an edge E, and this is one vertex V and another vertex V1 and V2. And you can you somehow distribute this M index to V1 and N index to V2. And then C, here you got index M1. Well, let's say at V1, you got a 1C, you got some M index 6, and this M index is contracted with this M index, and this N, then at V2, you got another C, N1, N6. Yeah, this N index are contracted at V2. Yeah, so here, this distribution of MN index at V1 and V2 is also clear from here, from these formula. So this M index is contracted with this invariant tensor C at vertex V. At vertex V here. So here is like we are putting M index around V and N index in another vertex. Okay, so this is kind of visualization of this kind of contraction. And here this C has another index I of V. So this I of V is just a basis. It's just labeling a basis in this invariant Hilbert space. Right? So this Hilbert space and the solution of this zero total angular momentum condition, it's not, well, you get multiple solutions, and it spans a Hilbert space. It spans a finite dimensional Hilbert space in general. Of course, sometimes you get only a one-dimensional Hilbert space, but most of the time you get multi-dimensional Hilbert space. Yeah, so then you can make a basis in this Hilbert space, and this I of V labels the basis. So here this I of V label. So this is the intertwiner basis label. Intertwiner basis. So it means that so this Cj, I, V, and Cj, the same J but different I prime V. If you make the inner product, in this inner product is for the this invariant tensor, or this inner product is, yeah, invariant tensor Hilbert space. So this is delta IV prime. So which means this I of V is just 1, 2, 3, 4. Yeah, so if just labeling the basis in this Hilbert space. So this Hilbert space is always finite dimensional. Just labeling the basis. Okay, and so here from this diagram, you can see how these Mn index are contracted. So which means this formula should be write down this formula, and you should contract Mn indices. Contract Me, Ne indices at all vertices. Okay, so here another remark is that so your graph has to be, the lattice has to be a closed graph. Okay. So it means that it has no dangling edge. So now we assume, so the lattice, assume the lattice gamma has no dangling edge. Namely, suppose you have a vertex. It's fine to have 6 valent vertex, or in most of the vertices are 6 valent. But suppose you have open edge, and you have one vertex has no, well, there's only, suppose you have a vertex which is endpoint on one edge, but it's not endpoint of any other edge. Because suppose you have a graph like that, and it all have connect to other vertices, but you have one open leg, one open edge, or what we call dangling edge. Then you can't have gauge invariant at this here. No, you don't have any, so no gauge invariant. No gauge invariant because, yeah, you only have a single angular momentum. Well, and there's no other angular momentums. This equation, you won't get any solution. Yeah. This equation, the only solution is trivial state, 0 states. The only solution is trivial state. You don't have any non-trivial state satisfying this equation. Suppose you only have a single angular momentum. So here you have a non-trivial solution because you have 6 angular momentums. But in this case, you have no angular momentum. So which means, suppose you have dangling leg, suppose you have dangling edge, your state cannot be gauge invariant. Cannot be gauge invariant. Okay. So which means in order to have a gauge invariant wave function, you have to assume that in order to that all the wave functions are gauge invariant, you have to assume that this gamma has no dangling edge. So which means the simplest case is that suppose our lattice has periodic boundary condition. Yeah, suppose, for example, gamma partitioning the torus. Partitions T3. In this gamma is lattice, which is a cubic partition of the 3 torus, and then it has periodic boundary condition, and you have no boundary. You don't consider boundary, and there's no boundary on T3, and all the edges are 6 valent. You don't have this kind of dangling edge. So this is the simplest case that we can consider, and of course, and that's a different story if you consider a boundary. All right. Okay. Let me see if I need to make other statement. Okay. So then this. So we have construct those wave functions, and these wave functions are actually the basis. So this T, gamma, J, and I. They are actually basis. They are again orthogonal basis. Orthogonal basis in H gamma in the Hilbert space of gauge invariant functions. Space of gauge invariant wave functions. Okay, so these are we have constructed the basis of wave of those of the Hilbert space, and this is also called spin network basis. It's called spin network basis. Spin network basis. Okay. So why is it called spin network? So okay, so before that, there is a simple homework just let you practice, help you to get familiar with this wave function. Homework to prove that they are orthogonal. Prove the inner product of H gamma prime 9 is inner product in H gamma, or this inner product, because H gamma is just a subspace of H gamma 0. So this you can compute by using inner product in H gamma 0. Result is delta so here this I put a vector I because I is also vector I is a sequence of intertwiners of I's at all vertices. So here, these gauge invariant wave function depend on the graph, or that is gamma. They depend on spins for all the edges, and also depend on the intertwiner at all vertices. Okay, so prove this, and this inner product. Right explicitly, this inner product H gamma or H gamma 0 is just integral product of edges Haar measure at H so this is just standard L2 inner product. So this is your homework. Just let you to let you familiar with this function T. Okay, so what is a spin network? So why we call it a spin network basis? Spin network. Okay. Okay. The reason is that this gamma, these data, gamma, J, and I, labels the basis. So actually, this label is called a spin network, and this function is called spin network function or spin network basis. Label basis in H gamma. Okay. So what are those? What that means? It means that firstly you have oriented graph, or oriented lattice. Oriented means that all the edges are oriented. So you have a graph where all the edges are oriented. So it's called oriented graph or oriented lattice. So in my notation, graph means lattice. Lattice means graph. Whose edges whose edges are colored by spins JE. This E are colored by spins JE, and vertices V are colored by intertwiners. IV. Yeah. So here IV, as I said before, IV is the intertwiner label. IV labels the intertwiner basis. So IV is so IV labels intertwiner. So IV you can also view that IV is an intertwiner because right. So I can for example in harmonic oscillator, this means a state, but N is just the label of the states, right? Yes, like so in harmonic oscillator, N means a state. It is actually a label of the state. So that's why we call this IV is the intertwiner. So we say that, so here this set of data is firstly you have a graph, and on all the edges of the graph, you assign, you color the edge by using the spin J, and on every vertex, you color the vertex by using intertwiner I. Okay, and you can draw a graph for that. So this is this is your cubic lattice for your graph. It's oriented. For example, you can orient it in this way.